So yeah, my name is Igor. I'm a first-year PhD student at the University of Lille, and today I'll be presenting a joint work with Bastien Cazot, Antoine Lemasset, and Camille Marchais about an exact and dynamic representation of k-mer sets named CBL. All right. So first, as a start, quick reminder. So we're interested in building a data structure to store k-mers, so strings of length k. And we want to be able, given such a string, to answer whether it's contained or not in our reference. So obviously, this is an essential building blocks in bioinformatics, and it's one of the core ingredients of many modern tools. So to start, so can you see my pointer? Oh. Yeah. Oh, okay. Thank you. Sorry for that. So as I said, I really like this figure. It's taken from the paper on SBWT by Alan Coe and others. And I think it shows very well the two main metrics that we're interested in when building k-mer sets. So the first one, obviously, is reducing as much as possible the query time. So how much time do we need to answer whether a k-mer is present or not? And the second metric is the memory taken by the data structure. So you can see here, there's kind of a Pareto front here. So you have this trade-off. Basically, some structures are very space efficient, but have quite expensive queries, whereas some others have very fast queries, but aren't very space efficient. Now, the goal of most papers is to sit in this bottom left corner, and many of the recent data structures are getting closer and closer to this optimal trade-off between time and memory. But it turns out that if we look more closely, almost all of these data structures are static. So what does it mean? It means that they're built for a fixed input, so for a fixed reference. And if we want to update it by adding new reads, new data, or just filtering some reads, we can't. We have to rebuild it entirely from scratch, which is obviously quite expensive. So our goal today will be to design this kind of data structures, but we want it to be dynamic. That is, it should support fast insertions and deletions without having to rebuild it from scratch. And on top of that, we'll try to implement fast set operation as well to be able to merge and intersect multiple indexes in a little time. So having this kind of operations is very convenient if you want to be able to build indexes incrementally. For example, you could just use adaptive sampling and add the reads along the way by selecting which one are relevant. Or you could just want to update your data with a new genome, for instance. So this kind of data structures allow it. Okay. So the first idea that we had to achieve these operations was to use a new kind of transformation that we call the necklace transformation. So this transformation was first introduced in the string algorithm literature, but it turns out that it hasn't been really explored in bioinformatics until now. So how is it defined? Given a string, so here I have a k-mer of size 5, we'll consider every cyclic rotation of this word. So for instance, if I take the first rotation to the left, I have GAA-CTC, then the second one will be AA-CTCG, and so on. And given all these cyclic rotations from my original string, I will select the one that is the smallest with respect to the lexicographic order. So one nice property of this transformation is that if you keep track of the number of rotation, it's completely reversible. And here, it would be the second one. So if we want to recover the original string, we would just need to do 2 rotations to the right. So in the paper, we introduced an efficient algorithm to compute this necklace transformation in a streaming manner by amortizing the computations for successive k-mers. And it turns out that we can achieve this computation in big O of log k, which is quite fast in theory, but it's also quite fast in practice, because on my laptop, I can just compute a necklace in almost 10 nanoseconds. Right. But you might be wondering, why are we interested in this transformation in the first place? Like, does it have any good properties to build a fast index of k-mers? Well, it turns out that if we look at, let's say, a dozen of k-mers of size 31, I highlighted the starting positions of the necklace here in color. I hope you can see it. And turns out that most of the time, necklaces of consecutive k-mers have a starting position that is just shift by 1. So if you look at the necklace representation and not the k-mer view, this is what you end up with. And it's quite convenient to have this representation. It's much better than the original one, because you might see it, but for most consecutive necklaces, there is only a single base that changes, and all the other bases are preserved. And in particular, if we look at the prefixes, here you can see that all these prefixes are the same. So we can exploit that. And in general, if you look at the size of the common prefixes for consecutive k-mers, you have these nice patterns that emerges. So the size of the prefixes will increase linearly almost always up to the maximum size, k31 in this case, and then it will reset, because at the end of this run, you start rewriting the prefix, so it will change. Now, we've seen that we have long common prefixes for consecutive k-mers, but how do we exploit it in practice? So the main idea of our data structures was to use quotienting. So here, if you look at these 3 necklaces, so just as before, they have a long common prefixes here in red and green. And instead of writing these prefixes for every k-mer, we only write it once and associate this prefix to a set of suffixes, which is much more compact. So if we look at the actual data structures that we design, so it's called Conway-Bromage-Lyndon, or CBL, and it's exactly the same structure. Like it has 3 main components. The first one is for storing the prefixes. So it uses a sparse bit vector to store the prefixes. So think of it as whenever I have a new prefix, I'll add a 1 in this bit vector. The second component here is a tiered vector. So this is, I think it's not that known, but it's a very useful data structures, because when you combine it with this bit vector and with a rank operation, you end up basically with an associative bit vector. So for every 1 in my bit vector, for every prefix, I can now associate data to it. And in this case, I will associate a pointer to the set of suffixes. So to store the set of suffixes themselves, they're stored together in buckets, and the data structures will depend on the load of each bucket. So small buckets will just use plain vectors to store the suffixes. But as soon as you start having many suffixes in the same bucket, we'll build a try to save space, basically. Okay, so how does what does a query look like with this structure? So most of the queries will share the following step. So given a k-mer X, the first step is always to compute its necklace representation. Then we'll split it as a prefix Q and suffix R. We'll look for Q in the bit vector, find the associated bucket with the tiered vector, and then query the suffix R in the given bucket, right? The nice thing about that is that we've seen before that most consecutive k-mers have the same prefix. So we can skip the first two steps if we know that the prefix is the same and just perform the operation on the smaller bucket, which is much, much faster and cache efficient. Right. So as an overview, let's recap the different operations that we can perform and compare it to some popular tools for storing k-mers or storing DNA in general. So we can see that most of the time, these structures are static. They only support membership and not insertion or deletion. Some of them do support insertion, but not deletion, so they're only half dynamic, I'll say. And very few of them actually support set operations, but we do support all of these. So now let's evaluate our tool in practice. So to evaluate it, we run a series of benchmarks, again, multiple of these tools. So in this example, we run the benchmark on collections of bacterial genomes taken from RefSeq. And you can see on the left, on the y-axis, the construction time versus the number of k-mers present in our data set. And in the second figure, you see the memory usage. So our data structures is the blue one, here and there. So you can see that it's not the best, neither in terms of query time, nor in terms of memory usage, but it's still very good for both. So I think it's a good trade-off. And most importantly, it's fully dynamic, whereas these structures aren't. Okay, so as a quick recap, you can think of it as something as fast as a hash table, or almost as fast, while it's significantly lower in terms of memory usage. So if you take, for example, a human genome, I think where it sits at like 40 bits per k-mer for k equals 31. On top of that, we also support, as I said, set operations. So if you look at the performances for merging collections, for example, you can see that in this case, it's a no match. It's both much faster and much smaller in terms of memory usage. Yeah, it's really well suited for this operation. And this is not the end, because there's still many other questions that are still open. And I think the first one that we can try to address is that I think the memory usage can be reduced further. If you look closely, the suffixes among the buckets are very similar to each other. So I think that we can compress them further to reduce the memory. So in practice, it turns out that almost all of the space is taken by these buckets. So this would be a major change, to a major improvement to reduce this suffix. And on top of that, I think that this structure can be easily extended. Right now, it's only built as a set, so we can answer membership queries. But I'm working on a new version that would be able to keep annotation with each k-mer. So for instance, you could store the abundance or the colors for a genome. And we could make a concurrent version of this data structure, so it would be even faster using multiple threads. And to give an example of what use case we can find with this new queries, basically, We recently wrote a preprint that shows how we can enumerate k-mers that satisfy a given constraint. So this is kind of the opposite problem. You don't start from a k-mer to find its information. In this case, you want to find all the k-mers that are, let's say, in genome A and B, but not C. Just an example, but you can write very expressive queries this way, and just it will list all the k-mers satisfying these specific properties. So to sum up, I presented a new data structure that is based on the necklace transformation. We've seen that it can perform fast queries because it's very cache efficient. It has a pretty good memory usage, though there's still room for improvement. And it supports wide varieties of operations, especially fast operation like insertion, deletion, and any kind of set operation. So if you'd like to try it, it's available on GitHub, both as a CLI and as a Rust library. So feel free to try it. I'd be happy to hear some feedback. And with that, I'd love to hear your questions and answer them. So thank you.
Thank you. So we have time for a few questions. Maybe I would start. So where is the name coming from of your data structure?
All right. So as a start, we designed it as a compressed version of the Conway-Bromage data structures. So this one is only built with no transformation, just indexing k-mers as plain integers. But we added this Lyndon transformation or necklace transformations. They're pretty similar. On top of that, and this is what brings all the locality and memory improvement over the previous data structures. So that's where it comes from.
Mm-hmm.
Thanks for the talk. Can you comment on cache coherence of the structures?
Yes. So we designed the bucket so that we designed the bucket so that each vector would fit in the smallest cache line. So whenever you query a similar prefix and you have a small bucket, it will stay in the cache. So this is where it comes from. When you have large buckets, you have to go through a trie, so it's not as efficient. Though every level of the trie is still laid out in a way that it would fit in the cache, but you may not fit the entire trie at once.
Okay. Any other? Yes, we have a question there.
Yeah, thank you for the talk. It was really cool. I had a question about if you were to change the size of K or choose a different size of K, you mentioned there's sort of a range of how many, like approximately how many bits per K would be needed for the representation. So could you just clarify what part of the data structure changes as you change K, and what is the sort of range that you can expect different values of K?
Yeah, sure. So let's have a look at the data structure. So in this case, you can adjust a second parameter on top of K, which is the size of the prefixes. If you don't change it, you keep the default size, the size of the suffixes will increase. So right now we represent the suffixes as bytes, but bit-backed k-mers for bytes. So if you increase K, it will add, let's say, 1 or 2 bytes to each suffix. But in the case of the trie, it will become deeper, basically, right?
So does the overall space depend on how much, or how long the longest common prefixes between necklaces are, and that's sort of data dependent? Is that right?
It's sort of data dependent, but we don't choose very large prefix size. So most of the time, consecutive k-mers will end up in the same bucket. What actually causes the change is that the prefix gets basically rewritten when you arrive at the end of the end of the series, basically.